the one this afternoon was kind of a little sidelight for a fun lecture because I'd done an article for the Wall Street Journal on the weekends section when the movie Exodus came out, and it was just for fun because the weekend's for light type stuff. And the director had used a tsunami for the parting of the Red Sea to make it more naturalistic, more realistic, only it didn't make any sense. And I had a theory that was mentioned in my book as kind of one of those little stories just for the fun of it, where the tides had almost drowned Napoleon about 3,000 years ago in roughly the same area that's supposed to have happened with Moses. So we'll leave that for now, and you can ask at the end if you want. But if you're very religious or you're very atheistic, I'll tell you, when that article came out in the Wall Street Journal, everybody was lambasting me from the left and from the right, when it was just a fun piece. But anyway, but today's talk, as part of the rising tide theory, series, you'll see in a minute, my Power of the Sea book deals with a lot of marine catastrophes, but I'm going to emphasize the storm surge part of it here and cover a little bit else after that, mainly because of the Dutch theme. They've been fighting storm surges for more than 1,000 years. Every time they would build some new land, a North Sea gale would happen, and the storms would come in and wipe out everything they'd worked on for 100 years. Likewise, because of our experience with Sandy, fresh in our minds, we can see what damage storm surges can do, and if you remember Katrina, what damage it did. But part of the theme of this, because this is a history, if you think Sandy and Katrina were bad, it's like night and day compared to what it used to be. Because basically, it's only been in like the last 50 or so years we've even done halfway good at predicting storm surges, and we're doing very good now. But prior to that, literally over the centuries, millions upon millions of people have been wiped out by the flooding caused by storm surges. And there are a few hot spots in the North Sea where the Dutch are is one of them, the Bay of Bengal, where Bangladesh and India and Myanmar are is even a bigger hot spot where literally 500,000 people died from one storm surge. I mean, that's incomprehensible compared to what we're dealing with now. Not that what we're dealing with now isn't still very sad when people lose their lives, but I'm going to try and show you the difference in how far we've come. Of all the things I talk about in my book, the tides will come first because that has been fairly predictable over the centuries, even crudely, but everything else in the book, storm surge is the one place where we've made incredible progress on predicting it well enough to save lives, predicting it well enough to have people evacuated. So this is the book, and the theme of the book essentially is when the sea turns its enormous power against us, our best defense is just get out of its way. We can't control nature. But to do that, you first must be able to predict when and where the sea will strike. Now, if this had been an academic book, it might have been called The History of Marine Prediction. But the idea here was to interweave stories of dramatic, unpredicted natural disasters with stories about how scientists and mariners very slowly learned to predict when the sea is going to try to kill you, essentially. So at the bottom part of this slide here, over to the left, these are all the different things sort of covered in the book in terms of learning how to predict them. And all the way over to the left is the tides, the astronomical tides caused by the moon and the sun. And it was so obviously connected with the moon and the sun that even in ancient times they would see correlations and they could sort of crudely predict it. Next was storm surges. And as I said, only in the 20th century have we been able to learn how to do that. And a lot of that's predicting weather and predicting hurricanes. So when we got to the end of the 20th century, we had satellites, numerical models, and that kind of stuff. That's when we finally got, predict them well. Next is wind waves. Also very difficult to predict. Only in World War II did we finally get a handle on it. And then the big topic still remaining is rogue waves, trying to predict when they happen. For a long time, it was even denied there were rogue waves. Then there's tsunamis. And you know about the 2004 disaster, 300,000 people roughly died around the Indian Ocean, mostly in Sumatra, in Indonesia. And then the more recent one in 2011 in Japan, where about 20,000 people died. And tsunamis are still unpredictable. And that's the reason being that you can't predict the underwater earthquakes that produce the tsunamis. Now what you can do is once the earthquakes happened, within minutes, because of seismographs, you can pinpoint where that happened. Then you run the tsunami model, and from that point on, you can predict where it's going to go, how long it's going to take, how big it's going to be. So the one off Japan was 60 miles off the coast. And if you were in Hawaii, you had some time, like 6 hours. But if you were in Japan, you had 29 minutes before that tsunami was going to hit the coast. So that's not very good prediction. The one exception, as you'll see at the very end of the talk, is if a volcano blows, you have some advance notice there. And like when Krakatoa created its tsunami, we could have probably predicted that today. But most of them we can't predict. The last part of the book is a little bit on El Nino and climate change, but that's more long-term prediction, and we won't even touch on that today. In fact, this is just to emphasize that if you got the book, it's chapters 3 and 4 that really focus on this. It starts out with the tides, then storm surges, then wind waves and rogue waves, then a lot on the tsunamis, a little bit at the end there. So throughout history, the ocean has risen to flood the coast, bringing death and destruction. The high winds from hurricanes and gales is what generates the storm surge. There's a little bit of low pressure effect, but nothing compared to the winds. Then the storm surge is like a big, long, huge, wide wave that kind of rolls up onto the shore. And then on top of that are the wind waves that make the news, because they're sort of riding on top of the storm surge and crashing onto buildings and stuff. And they do damage, of course, but they're riding on the storm surge. You've probably seen this picture a million times. It's that Hoboken taxi parking lot flooded by Sandy. You can see the waves crashing up by near the George Washington Bridge. Up on the top left is a whole bunch of weather models making predictions 42 hours before Sandy struck the Atlantic City area. This kind of thing could never have been done 20, 30 years ago. So we've come a long way, and even though the models don't always agree until you get within 2 days, they're still doing so much better, and you're getting so much leeway. And you can see in the bottom the actual storm surge versus the tide and that type of thing. So today I'm going to talk storm surges, but I'm going to start with the tide first. The Dutch also have done many, many things with the tide, because tide prediction's critical for a couple of reasons. One, the storm surge is on top of the tide. If the storm surge happens to hit at high tide, it's going to do much more damage than at low tide. In the Gulf Coast, there's not very big tide ranges, so it doesn't matter. But someplace up north, if the storm surge hits at low tide, it won't do nearly as much damage. So tide prediction is critical, but in the past, it's always been critical even for its own purposes. There are dangers just due to the tide. There are places like here, Bristol, in the UK, with 40-foot tide ranges, Anchorage, Alaska, Bay of Fundy, a whole bunch of different places. And there are places where if you're at low tide and the tide comes in, you can actually drown. There's tidal bores in some rivers. There's tidal whirlpools, a whole bunch of things. So the earliest predictions were for the tide by mankind for a variety of reasons. But at least the tide's predictable, and that's because of the astronomy behind it, the moon, the sun, that type of thing. So even ancient civilizations could crudely predict it. This is near Anchorage, Alaska. It's low tide. That's a 6-foot guy standing there. That is a 40-foot tide range. And if you happen to be, as often happened back then, I mean, even in the last few decades, hunters would go out to hunt there, and they get stuck in the quicksand. And then the tide would start rising 6 feet an hour. So within an hour, it's over your head. Pretty soon, if you're shooting with a shotgun, you're breathing through it like a tall straw as the water goes over your head, and it's freezing cold. And luckily, nowadays, the Coast Guard is aware of this. People have cell phones. They get out there in a helicopter, and they get you out of it. But there have been many people that died, and that's just one type of situation. The place that people normally ran into this were shell fishermen who wanted to go dig up mussels and clams and things, and then had to get out of there before high tide came. And that's what happens around a place like this. This is the Gulf of St. Malo, France, off the English Channel, 45-foot tide range. When it's low tide there, literally hundreds of square miles become like muddy, almost dry areas. And nowadays, they'll go out in really fast tractors, go out, dig it up, and get out of there before the tide comes in, because when the tide comes in, for centuries, they've described it as like arriving like galloping horses, swiftly encircling that abbey, which was built in 1708. So basically, the shell fishermen get in there and get out fast. They have to know the tide predictions. They have to know when low tide is and when the tide's going to start coming back, because in some places, when the tide comes back in, it doesn't gently rise. It rushes in and gets you. But there are other things like tidal bores and rivers that start out wide and narrow down, and that usually builds up the amplitude and distorts the tide, and friction tries to wear it down, but that further distorts it. The wavelength of a tide, which normally in the ocean is like 1,000 miles long, and it's not very big, and it propagates over the ocean, and it hits shallow water, it gets bigger, it goes into bays, it gets bigger, it goes into rivers, it gets amplified, and the wavelength shortens, and it becomes like a perpetually breaking wave that just runs up the river. And when Alexander the Great was there in 325 AD, he just conquered most of Asia, he'd conquered most of India. He was taking his ships down the river toward the Arabian Sea because he was kind of an amateur scientist, and all of a sudden he hears this thunderous roar that was like twice as loud as the elephants of this army he had just defeated. And that elephant's roar had scared his men. Well, this scared his men even more, and it was disrupting the ships and flipping everybody over. And it was, he escaped, and luckily most of his people escaped, but, and he knew nothing about the tide because the Mediterranean didn't have much of a tide. The most famous tidal bore, though, is in the China River of Qingtang, where, again, you can see how wide the bay is over here, and it narrows way down, builds up the amplitude, gets really distorted like it's always breaking. Of course, back in then, this is like 1056, some of the Chinese scientists, had figured out the correlations with the moon and other things, and they came up with the world's first tide table to predict when this tidal bore was going to come up. But the locals preferred myths and legends, and they believed that this Wu-Tu Zoo, a statue of which is next to the pagodas right now over there, had been thrown into the river as a disloyal member of the Prince's Guard, even though he was loyal, and it was his spirit that supposedly created these tidal bores twice a day. So there's plenty of legends that connect. And I was over there myself, and this is a picture I took of the tidal bore moving up the river. Unfortunately, I was there at neap tide. Neap tide is when the moon and the sun are not working together, so it wasn't the greatest tidal range. So it doesn't look that huge here, but it is still a little weird to see this wave cover the entire width of a 2-mile wide river just moving up the river. And sometimes it can be slow and undulating. This is in Sumatra, in a river there, and it wasn't quite as extreme, but it created all these beautiful undulations that people could surf on. But sometimes even the tourists get caught. This is where the tidal bore in that same place in Hangzhou, China, got a little larger than the tourists expected and just kind of went over the walls and washed people, who were watching there, because people go every day to see this. They never get tired of it. It's twice a day. Certain times of the year, like the fall, it's even bigger because of stronger tidal conditions. They have family reunions and everything there, but occasionally the winds and what might be called a very gentle storm surge can change the depth and change the characteristic of the tidal bore and make it even. There's also tidal whirlpools. Besides tides going up and down, tides go horizontal, into bays, out of bays, through straits, that type of thing. They can get very fast, these currents, going through narrow straits. And this is the Strait of Messina between Sicily and Italy. It gets going very fast there. This one's up in a variety of places. This is up near Scotland. Oops. Frequently, they can get so big that it would pull boats underneath. And this particular one is a real one that's happened that actually got into Homer's Odyssey. When Ulysses was going through this strait, he was worried about two monsters, Scala, which was like an eight-headed snake-type monster on the shore, and Charybdis, which was this ocean monster which would suck in all the water. Well, that was his name for this tidal whirlpool that actually could suck ships underwater. So the dangers of the tide are real. They're even real still today if you're not paying attention to the tide predictions. I showed you the Anchorage thing where hunters would get stuck in quicksand. Morecambe Bay is up in the UK between UK and Ireland near the Irish Sea, has a 30-foot tide range. It's famous for its cockles, which is a kind of a shellfish that, is expensive and people like to eat them. And back in 2004, there were 23 Chinese immigrants plus their Chinese gang boss who decided to take them out at low tide and dig these up for the money. But either he ignored the tide predictions or knew nothing about it, but all of a sudden it started getting dark and the tide started rushing in around them. And they had cell phones, some of them, and they were calling for help in the dark, and it was the saddest thing, and they all drowned. And there was a movie made called Ghost that was made about it, and it really affected how immigrants were treated and that type of thing. But the tide can still kill today in some places. But as I said, predicting the tide turned out to be easier than almost anything else. The ancients first made the connection between the tide and the moon. They noticed if they were up at night that it got higher tide roughly at the same time the moon was overhead. And even more importantly, they noticed that when the moon was full and bright, you'd get the highest tides and the lowest tides, and that was the biggest tide ranges. And it would also happen at new moon when the moon was dark. So they had a way of trying to figure out what the tide was going to be, and that could end up, saving lives. And as I said, the fishermen wanted to know low tide for digging up shellfish. The sea captains wanted to know high tides so they could safely bring their ships out and not run aground. There are really fancy artistic things like this Bruskin Tidal Almanac from France. This is part of the English Channel, which everything was always making connections when the moon was overhead and how many days after full moon and that type of thing. But no one really knew what caused the tide. They just saw the correlations. And people had theories. Galileo had a theory, almost got him killed, because Galileo's theory put the sun as the key producer of the tide, and he believed in the Copernicus theory, and so he was put on trial by the Inquisition because he was supporting Copernicus, and they didn't sentence him to death, but he was kept in his home for the rest of his life because of that. The ironic thing was his theory was wrong. He wasn't even considering the moon. Kepler, who's famous for planetary motion stuff, he realized it was the gravitational effect of the moon that was most important, but he couldn't figure out why there were 2 high tides a day in most of the world. René Descartes was totally off base. He believed in the ether, and the moon moving through the ether was supposedly causing the tide, not realizing that it would have been opposite. The moon would have caused a low tide when it was overhead rather than a high tide. Isaac Newton was the one that finally straightened it out. He understood the gravity. He understood that it was really a balance between gravity and centrifugal force. I won't get heavy into real science, but right here, if you see this yellow spot in the middle, that's where the Earth and the moon are both rotating around that spot, even though it's inside the Earth. And at that point, it balances. On the side closest to the moon, gravity is stronger than centrifugal force, and on the opposite side, centrifugal force is stronger than gravity, and that creates 2 bulges, 2 high waters a day, unless the hydrodynamics of the basin changes that. So tide prediction tables, and there were plenty of them in the colonies, for example. Almanacs were the most popular book after the Bible being sold. You've heard of Poor Richard's Almanac by Benjamin Franklin. He had tide tables. This table I'm showing here is Benjamin Banneker. It's an almanac and tide table for Pennsylvania, Delaware, Maryland, and Virginia, and he was a free African-American who lived in Baltimore. He was a self-educated scientist, astronomer, inventor. He did his own astronomical and tidal calculations for his almanac, and then he always had little footnotes that were very socially conscious, like, slavery is wrong, and, various things about what black African-Americans had accomplished and that type of thing. So, and as I said, in the colonies, fishermen had to know about it for fishing. Sea captains had to know about it. They were forever using the tide to trick the British during the Revolutionary War. They would sucker them into bays that when the tide was going down, they'd get stuck, and then they could just come in and take the ship because they were stuck in low water, and they didn't know the tide, but the colonists did. But on one particular night, they blew it. They forgot about the tide. Tempers were raging. It was the night of the Boston Tea Party. They dressed up as Indians. They went to these 3 ships that were next to the dock, not realizing that it's what we call a perigean spring tide, which means not only the moon and sun working together, but the Earth is closest to the moon as can be. It's the highest tides, but also the lowest tides. And that ship you see there by the dock, it actually was aground. It was in 2 feet of water because the tide was so low. They started dumping the tea over the side, and it started building up like bales of hay next to the ship. So they weren't really getting rid of the tea, so they had to jump out in the muddy flats and try to thrash it with their oars. For days, piles of tea were floating in Boston Harbor, and they're trying to get rid of it so the British will think they've destroyed all the tea. Anyway, and to get away from the science after this, Laplace was the next guy who really made a difference, a French guy. He was actually hired by Napoleon, and I talked about him a little bit this afternoon. But he explained there were 2 aspects of the tide. One's that astronomical forcing, the gravitational centrifugal force thing with the moon and the sun and that type of thing. And the other is the hydrodynamic response of the ocean and the bays and the rivers to this long wave coming in from the ocean. Tide's very small in the open ocean, but then it gets into the shallow water, and the dynamics of it can really amplify it till it can be like a 50-foot tide range in the Bay of Fundy and that type of thing. And so there's lots of different astronomical frequencies. You've got one that deals with this spring tide, neap tide thing, the fact that when the Earth and the Sun are lined up with the moon, there's a stronger tide versus at a 90-degree angle. There's how close the Earth is to the moon. There's whether the moon's over the equator or north or south. There's all these different frequencies. And Lord Kelvin in England was the one that realized I could take all these frequencies and kind of set up this pulley system and create this beautiful brass machine. And believe it or not, this machine, it may take a little while longer, can predict the tide as well as any computer today. Has all these different gears representing all these different frequencies. It was used during World War II along with American tide predicting machines are also beautiful to see. And even in the book, there's some story about the tide predictions for D-Day that relies on this and some other things. So now we're finally to storm surges. And storm surges, as I said, are going to now come in and be on top of that tide, but they're not going to be as predictable as the tide. In fact, they're virtually unpredictable until late in the 20th century. As I said before, that literally killed millions of people, and we're going to see a little bit about how far back this goes. This is Lothal in India, the Gulf of Cambay. It was destroyed by storm surges 4 different times. We've figured out from archaeology the worst time in 1900 BC. That actually is a tide lock where the tide rises up, they close it off, the water stays up there, and the ship doesn't go aground. And so they knew about the tides as well, but the storm surges they couldn't predict. They didn't know when they were coming, and it was usually disaster. Now, the interesting thing is you've heard about Noah's flood, whether you believe it or not, kind of thing, in the Bible, in the Quran. The fact is there's worldwide flood stories in many civilizations. India is one of them, the Greeks, the Hebrews, the Muslims. The earliest one goes back to 2075 BC. The Sumerians lived in the Euphrates River, and then the Babylonians came later. So there were a whole bunch of these flood stories. So I kind of touch on that only because it's kind of interesting to look at some of these past stories, whether you call them myths or whether you believe in them or not, and see if there might be a physical reason for some event that kind of inspired that story. And I did that with the party in the Red Sea this afternoon, but Noah's flood actually is one that has an interesting thing, because if you look at, I mean, every book is different. You've got Genesis saying you had 40 days and 40 nights. The Greek one says 7 days and 7 nights. But the interesting thing is that it says in the 600th year of Noah's life were all the fountains of the great deep broken up. That's water coming from the ocean, and the windows of heaven opened up. Well, that means the rain coming down. So the rain falling on the Euphrates River, actually, even if it's 40 days worth, wouldn't have been much. It wouldn't have made too much of a flood. The one country that doesn't have one of these global flood stories is Egypt, where they actually loved the floods of the Nile because it provided nutrients, it helped their agricultural things. So here's a country that was used to floods. It was no big deal, no big flood stories. So the Euphrates probably, it wasn't the rain, it was the storm surge. Well, why could that possibly be? Well, back in 2007, there was a Category 5 cyclone called Gonu. And it was in the Arabian Sea, it headed for the Persian Gulf, but you see this very narrow entrance here. It couldn't get through that, essentially. The friction of the land just tore it all down. But like 3,000 years ago, sea level was actually higher back then. It has nothing to do with global warming or cooling. It was tectonic action. The land was lower then. In the last 3,000 years, it had been raised up. So sea level was higher, and that entrance was wider. So now you kind of envision, what if a Category 5 type cyclone worked its way up into the Persian Gulf and created this big storm surge that went up the Euphrates and covered the low-lying lands? And it's not that inconceivable. For one thing, there aren't that many Category 5 cyclone that we even hear of. This before 2007, there were two others recently, one in 1890 and one in 865, so they don't come that often. And the rarer things are, the more they're going to turn into some kind of legend or story that people repeat. And so it floods the land, and if it's a low flat area, it goes to the horizon. It looks like the whole world's covered, even though it isn't. The stories of Noah's Ark says if it was true that it was carried north toward Armenia, that would be more a storm surge thing than river coming down a river. So it's just one of these things, and that's just interesting to deliberate on. There's more details in there. But you know, storm surges are happening all over the world, and each country, especially in ancient times, you know, China's figuring out things very early on. In the 5th century China, tropical cyclones were first recognized as a special kind of storm. They didn't know it was a rotating storm, but they did know that the wind seemed to come from 4 different directions at different times. And if you envision a rotating storm counterclockwise in the northern hemisphere, like a hurricane, like a cyclone or a typhoon, different names in different parts of the world, that depending on where you are, the wind could be in different directions. And so Yufeng was a wind or storm that comes in 4 directions. That was the earliest word back in the 5th century. Then there was Dafeng, I'm not pronouncing this right, but Dafeng Yuji Hei Chao, strong storm driving a sea surge. Of course, they had their prediction methods that didn't make sense. One was, before it comes, roosters and dogs are silent for 3 days. So they weren't being too scientific there. But eventually, they started seeing what they call Ling Feng, a preparatory wind, and warning signs were called Jimu for, you know, anticipating a Yu Feng coming. But they recognized these storm surges were the most dangerous part and most dangerous at high tide. So the Song dynasty back from 960 to 1279 AD actually kept official records of what we would call hurricane landfalls, their storm surges, casualties, property, the whole thing. And Japan, it was not free of them either, but they actually had a couple of benefits, and because of the benefits of it, they call it, that kind of storm, divine wind or kamikaze. And the reason they call it that, on 2 separate occasions, and this is the sheerest of luck for them, Kublai Khan of Mongolia brought huge fleets with him, including ships from Mongolia, Korea, China, to attack Japan. And in both instances, in 1274 and 1281, he was mesmerized, he was virtually destroyed by what we call a hurricane, a cyclone. And so ever since then, they called it kamikaze or divine wind. And some of it was the wave action, some of it was the storm surge. It was just the Caribbean also, as you know. I mean, we have hurricanes all the time in the Caribbean, but it goes back a long distance as well. In his second voyage to the West Indies, Christopher Columbus even ran into one in 1495. The Mayans had a wind god called Huracan, and their symbol for the windstorm is that symbol with the face up in the right-hand corner, which seems to imply rotation. We don't know for sure. The modern symbol for rotating like a cyclone is the thing on the right, and it looks kind of similar. But we really didn't start learning till we get to Holland, the Dutch, the Germans, all the people living on the North Sea, the British. Storm surges were produced by North Sea gales, tens of thousands killed by a single storm kind of thing. This etching was made in 1683, but it dealt with the 1638 storm surge along the North Friesland coast of Germany. Here's another one, the Christmas flood of 1770 around North Sea, which is somewhere along one of the Dutch coasts. These are just some of the storms over those years. That 1717 Christmas flood killed 14,000. The 1634 what they call second Grota Mondragon, called 15,000. There was 40,000 in the one before that, 15,000 St. Peter's flood, 36,000 killed another time, 80,000 in 1287, 100,000 killed in 1530. And these are just estimates that are probably not as many as you would think. You can see all those storms. The 1703 storm just said thousands. They didn't even know what that was. All because of these strong North Sea gales pushing up these storm surges. You'll probably have heard that, like the Netherlands, Holland was always reclaiming land, building these, making these polders and these various things, and they would build up land for 100 years, and one storm surge would come and wipe it all out, and they'd start all over again. But this doesn't even compare to the Bay of Bengal. Death tolls. 1737 in West Bengal, which is now Bangladesh, 300,000 killed. 1839, another 300,000 killed in India. 1864, 80,000 in West Bengal. 1876, 215,000. I mean, these numbers are incomprehensible when you think about them. 1897, another 175,000. 1970, there were 300,000 confirmed dead in East Pakistan, which was soon to become Bangladesh. Probably 500,000. In 1991, once it is Bangladesh, another 138,000. And a lot of this is because it's low-lying land. There are populations living in huts. And the horror is just kind of immeasurable to figure that many families. Let me go up. Yeah, I jump ahead and I'll go back. The largest natural disaster in the United States was the Galveston storm surge in 1900. 6,000 bodies found, probably 8,000 dead. It knocked out all these homes, and if you read the book Isaac Storm, you get some feel for the kind of families living in those homes and that kind of thing, and the horror of it. But if you, let's see, I got to keep getting back to where I was. If you get back to this, and to compare like the 8,000 dead in Galveston with people in pretty strong homes, and now you imagine just literally thousands and thousands, maybe 100,000 small huts with people shivering in fear inside because of the strong winds, not even realizing this big, long, huge wave is about to wipe them out. And some of the stories when they're being, now the ones that survived the drowning are being pulled through the jungle and trying to grab on branches, and you see tigers floating next to you. It's just, it's just kind of incomprehensible. Now, to predict the storm surge, you had to be able to predict the storms. So this is where the weather, where meteorology comes in, and some of the beginnings of trying to figure out how to predict the storm surge means how to predict the storm. A good old Ben Franklin, in my book, he's about 5 different places. He really was a genius. He came up with so many things. He was a guy that maybe the first one that realized that a storm was a moving system of winds, and the storm might move in a different direction than the wind direction itself. And this had kind of happened because he was looking forward to seeing an eclipse one night that's supposed to happen in Philadelphia, and it was cloudy, it was terrible, it was raining and stuff. Yet his brother in Boston saw it perfectly, it was perfectly clear, yet the wind was coming from the northeast. He said, that's strange, my brother's in Boston, the wind's coming from that direction, what's going on? And that's when he realized it. And then he had another brother who was closer, I guess down in either Washington or Virginia, who also had clear weather, and he started realizing that what was happening was the closer you were to the Gulf of Mexico, the worse it was. And the storm was actually coming from the Gulf of Mexico, even though the wind directions, he didn't know about rotation yet, was coming from the northeast. And he had this analogy of a chimney. And he said the Gulf of Mexico is warm, the air goes up, the air comes in, it creates these storms. He got pretty close to what was really happening. But it took William Redfield and the famous 1821 hurricane, the last hurricane, to pass over New York City. It created a storm surge of 13 feet that flooded lower Manhattan. And the reason this was important in the annals of science was that Redfield had gone through parts of New England. He was going to where his wife died. He walked with his son. He saw patterns of trees knocked over, and the direction that the tree was knocked over by the wind was in different directions in different places in New England, and he realized it had to be a rotary flow, the first cyclonic flow, and the first proof of that. And the debate went on for years with other scientists. Joseph Henry, who started the Smithsonian, he made the biggest contribution because he realized that because of what Franklin said, and Redfield to some extent, that storms move, and if he had a telegraph network of weather stations across the U.S., he could actually see the storms move and stuff. And so it's almost real-time weather. It was the first close to real-time weather system set up and made a big difference in understanding it. And Fitzpatrick over in England, a couple other people started doing the same kind of thing. Now, on that previous slide of Bay of Bengal, I had the 1864 storm in West Bengal, 80,000 dead. This was the one that really made a difference, though, because now the British had moved in. They'd set up an Indian meteorological society, and they started taking data and had eyewitness accounts, and they made measurements, and they had measurements from the ships that were out on the Bay of Bengal, and they started realizing about cyclones and storm surges, and it really started the whole thing going. Okay, so back to Galveston, our biggest natural disaster. It didn't necessarily have to be that way. It turns out that Isaac was really a river type scientist. He didn't know anything about storm surges or hurricanes. Meantime, there was a group down in Cuba of priests who really were studying hurricanes, and they actually had forecast that one hurricane was going to cross over Cuba and head up toward Galveston. And in the politics of science, even back then, the Washington office of the National Weather Bureau kept that information quiet and basically didn't give them the correct forecast because they didn't believe it, because it's just a bunch of priests in Cuba, they said. And lo and behold, this was the result. So things started to change after that. In the North Sea, there was a big storm in 1953. It flooded a lot of parts of Holland, the Netherlands, Great Britain. There's the upper right-hand picture is a picture of a boat that, well, you heard of the kid putting his finger in the dike to stop a flood. Well, this was the guy that put a boat into a hole in a levee to keep Rotterdam from getting flooded. So there were 1,800 deaths in the Netherlands, 307 in Great Britain, which is not a lot for that time, but they ended up building these big gates to try and close when the storm surge is going to come in to keep the flooding from happening. They're still in operation now. So the 1970 storm in Bangladesh, the storm surge that led to the birth of a nation. It was when the Brits left India, as you probably know, it was broken up into the Hindu section in the center and two Muslim sections, West Pakistan, East Pakistan. Well, East Pakistan was actually Bengalis who'd been converted to Muslim. And the West Pakistan was really close, Middle East type feelings, and they looked at East Pakistan as kind of second-class citizens, even though they're part of, their own country. So when this storm surge hit in 1970, West Pakistan really didn't help East Pakistan. Instead, it was India, who's supposed to be their enemy, helping, the United States helping, Britain helping, everybody going in there and helping. The devastation was absolutely incredible, but it turned out to be the straw that broke the camel's back, and so there was a revolution, and East Pakistan broke away and became Bangladesh. There's more about that in the book, and then there's even very interesting books written about that whole revolution. So what's the difference now? I briefly said it before, but satellites, really huge thing. With satellites now, you can see the weather systems. You can see the hurricanes moving. Even if your models aren't that good, all you have to do is follow it in real time and know where it's going to hit, that type of thing. Computer power has gone up. Weather models have improved. As the computer power goes up, you get more physics in there, you get higher resolution. If you get the weather right, which produces the right winds, then the ocean model, the physics there is really solid and stuff. You just need the right winds to drive that ocean model, and you'll get the storm surge. So literally, this is the kind of thing, and the Dutch played a big role in those water models. The European Center and the United States Weather Service and various universities have played big parts in improving the weather models. Right now, the European seems to be a little better, and nowadays, when you look at, like when you see that thing I'll show again with Sandy, there's like tracks of 20 different models, and in that one, they're sort of all agreeing, but a day or so before, the European model was doing better and saying it's going to turn and that type of thing. So now it's really kind of fine-tuning. If we get the winds right, we'll get the storm surge right, and then you'll see it's just a matter of communicating that to government officials so that they act correctly. In fact, it's even made a difference in the Bay of Bengal. In the Bay of Bengal, between us, Europe, and India, we start providing very accurate predictions of forecasted storm surge to the various countries. And on top of that, part of the problem was not just knowing it was coming, but where do you go? In Bangladesh, low-lying, where do you go? You're living in huts. They started building cement, strong buildings that were centers that people could go to escape for when the storm surge came through, and that really made a difference. Sorry, talking so much can get your throat dry. So, in comparison to previous deaths, for example, a big storm surge hit Bangladesh in 2007, and only 3,400 people died. And I put the only in quotes because no one wants anybody to die, but compared to like 100,000, that's an incredible thing. In 1999, in India, who learned a little sooner how to communicate about the storm surge coming, 9,800 died there. However, in Myanmar, which was still run by the military junta, who refused to give the information of the storm in 2008 to its citizens, 146,000 people died, even though they had predictions on the storm surge hitting. So you can see how the prediction itself is only so good as the information passed on to the people to make a difference. It brings us to Katrina, largest storm surge in U.S. history, even larger than the Galveston one, 27.8 feet at Pass Christian, Mississippi, which is the same location previously had the record. There's just something about the hydrodynamics of that section. As you know, it hit New Orleans August 29, 2005. The model forecasts of Katrina's hurricane track and the size of the storm surge were very, very accurate. And NOAA started getting really hot about serious warnings 4 days before landfall to make sure the government fully appreciated it. We know about the levees not meeting the challenge, and the governments didn't meet the challenge either, and there were fatalities that never should have happened on that. Hurricane Irene, which was the year before Sandy, it had a track that was almost like that 1821 hurricane that hit the New York City, went right over it, and caused a huge storm surge. In this case, it was a different sort of hurricane. It weakened. It mostly dropped tons of rain on New Jersey, and there was lots of rain-type flooding and that type of thing. Even so, New York City had said, well, evacuation zones 1 and 2, or A and B, however you want to call it, should evacuate. Turned out there was not much of a storm surge, and so, some people looked at it like, oh, we shouldn't have evacuated. But then Sandy comes, and this is definitely one that caused a huge storm surge. You can see right there in the red, the tide plus the surge, how high it got. And for some reason, New York City only made the first zone evacuate, not the second zone. As it turned out, my condominium was in the second zone, and it got flooded, and the water went down into the basement, and 70 cars got, ruined and that type of thing. It's still, all this is minor compared to deaths and things like that, and my wife and I had left for Virginia, knowing, because we used to have a house there, that it would be much better in Virginia than New York City. As it turned out, it was true. But it still was a place where the predictions were very accurate, with at least 42 hours notice that this was going to happen, and somehow, you have to communicate it in a way that government officials will understand what you're communicating so they can take the proper actions, and that's something that still has to be worked on. Here are the evacuation zones for New York City. You can't see the difference between the red and the orange, but they're right at the edge, and we were in the orange one, and they really should have said evacuate orange as well as red, but for some reason they didn't. So we can now predict storm surges and the hurricanes and gales that produce them very well, and we got the satellites to double check what we're doing. How well can we predict those other potentially destructive marine phenomena that I mentioned in my book? Waves, rogue waves, tsunamis, all that type of thing. And it's just the book chapters, the different things in. Tsunami prediction. They're not predictable, as I said before, because the submarine earthquakes that generate tsunamis are not predictable. Only when a submarine earthquake happens and its location is identified quickly can the warning system go in and say, watch it. But for Japan, that didn't help much. 29 minutes before the tsunami hit. In fact, here are 3 tide gauges along Japan. And one tide gauge, the one closest to the worst part of the tsunami, was destroyed 29 minutes after the earthquake began. And the other 2 just some high-frequency stuff up north and south. Likewise, you've heard a lot about maybe these dart buoys put all around the Pacific to measure the pressure field of a tsunami going by. And again, these work well if the actual earthquake is pretty far away and it gives you some warning. But here it was 33 minutes when you saw that pressure change as it went by that particular buoy. This is the 2004 Indian Ocean tsunami. 230,000 died in the first 30 minutes, almost 300,000 in the first 2 hours. Most of them are up here in the northern end of Sumatra. The ones that died in Thailand, there was a few, about 7,000 or 8,000 there. That got the most publicity in the beginning because of the vacationers. It went in the stars are the fault, this very long fault, and where the bottom shifted, and then the tsunami went both east and west. The westward propagating stuff, this is where it was after the first hour, the second hour. So it hit Sri Lanka about 1.5 hours. It hit India, and there were deaths of 20, 30,000 each one of those places. And then as it gets further and further, there were a few people died in the Seychelles and that type of thing, but it was smaller and smaller as it went by there. Because you can't get fast predictions. I mean, right here in the northern part of Sumatra, it was 15 minutes before this 100-foot tsunami crashed on the shore. And the people didn't know better. They saw the water recede, because typically the water recedes first in a lot of tsunamis, and then the big wave comes and it gets you. Well, the water receded and they ran out onto this dry bottom. They caught the fish that were flapping on the bottom. They looked at the dry coral. They were amazed, and then they saw this wall of water heading for them, and it was all over. In fact, even the ones that knew what it meant and started running, it was probably all over when a 100-foot high tsunami hit you. In Thailand, it was maybe 7, 8 feet high. It had gone quite a distance before it got there. But ironically, so it points up, you got to be aware, if you see the sea recede and you're in a place like this, just play it safe, run inland. And this was actually taught in certain places. This island here, I pronounce it Simule or something like that, but these people, through their generations of the grandfather telling the kids the story of the last time it happened, they all knew what to do. There was 80,000 people on that island. It was the closest thing to the bottom edge of that submarine earthquake, and only 2 people died out of 80,000 because they knew what to do. Likewise, the Moken Sea gypsies, they knew either go up to the top of the hill or take your boats out into the middle of the ocean where the tsunami's not big. And in the Andaman and Nicobar Islands, the Stone Age tribes, they knew what to do. And then when the Indians, it's owned by India, when India sent helicopters to see if they're okay, a lot of arrows were shot up at the helicopters saying, leave us alone, we know what we're doing. The only place that sometimes you might get a warning is if a volcano blows. Krakatoa blew in 1883, and it was such a big thing, it created a huge 50-foot tsunami, killed 35,000 people. It also is interesting because it was like the first global story, because just prior to that, all these underwater cables have been connected, and whereas it would take 2 weeks for a story about Indonesia to get to Boston or London, now it took only 4 hours. It's kind of like the Victorian internet, because Queen Victoria was in power at that time. But then the tsunami actually broke the cable and they had to fix it. But in the meantime, scientists from the Coast and Geodetic Survey in the United States in San Francisco had seen this like blip on their tide gauge, and they figured out it was from a tsunami somewhere in the Indonesian area. It had to have been that one, and they could tell from the size of the blip that it had been a really big tsunami. There are other things we know too that help. For example, I showed you where Sri Lanka got probably hit an hour and a half after the tsunami started over by Sumatra. And at the east coast, when you look at this town here, only 2 people died. When you looked at this part of the coast, at this city, 8,500 people died. What was the difference? The difference was this was near a submarine ridge, and this was near a submarine canyon. And it turns out because they're long waves, they get focused, and they propagated along the ridge and were made larger by the ridge. And the energy was spread out in the canyon and was very weak when it got to this city. And it was almost like the tide just slowly rising and falling. So there are things we know that can kind of help minimize some of the damage of tsunamis, but we still can't predict them. Wave prediction, by this I mean wind wave prediction, has been another difficult one. And here again, Ben Franklin was involved, and he had certain things like he was on this ship, this British ship. They were going to attack a French fort in Nova Scotia. And he noticed that behind his ship, the water was pretty smooth, but behind the other ships, it was really choppy, not just big waves, but choppy. And the captain came up and said, well, the cook must be emptying the greasy water through the scuppers, almost disdainfully, like, you should know this. What's with you? This always happens. Well, it turns out that the greasy water on a water surface keeps these little capillary waves from being started because it changes the surface tension. The wind can't grab it, and so it can't start building up the waves. And Ben Franklin studied this and figured it out, and he even used to play jokes on his friends. He would go to, when he was in England, he'd go to these ponds where the wind was blowing and creating waves and stuff, and he'd hidden a little thing of oil, fish oil, in his cane, and he would wave the cane over the water. The oil drops would drop on the water, spread out in a real thin coat. The waves would disappear, and he'd say, abracadabra, waves go away. And sure enough, they went away, and he figured, God, the guy's a magician. But he came up with a theory 200 years ahead of time in terms of resonance. I won't go into that now, about what makes waves get so much bigger, why they keep getting bigger and bigger with the wind. But what about the really big ones? Near shore, the shallow water causes them to get bigger. And if you're offshore and the waves are going against the current, the energy from the current makes them bigger. Bermuda Triangle probably got its reputation initially because of the big waves that sank this marine Sulphur Queen ship. And it was because the big waves were going opposite the Gulf Stream and flipped it over, but it was the beginning of the Bermuda Triangle thing. But we still can't predict rogue waves out in the middle of the ocean. And there's definitely times where it's happened. There was this troop ship in World War II that almost capsized with 15,000 American soldiers on it going to England in World War II. And those are the kind of things that they haven't quite figured out, but the wave models are getting better, the physics are getting better. I think we're pretty close to that. So I think that's it. That's an abrupt way to end. But I want to just touch on a few of those other things we're not quite able to predict yet. We've done a great job on storm surges, and we need to fine-tune it a little bit so the governments understand them better, and the Dutch played a big role in that. Thank you.
So the models have been working better and better over the decades, but now we have superimposed on all of it climate change.
Well, it's not really superimposed because climate change is such a slow changing process. The only way you could say it superimposed it is, was it responsible for making that hurricane a little stronger? Or was it responsible for making sea level slightly higher? And that would all look like kind of either the size of the storm which we're dealing with because we got the weather, or it'll look like, the change in bathymetry or depths or something like that. And so it's not, strictly speaking, superimposed. And then that begs the question whether you even believe that, because the statistics in terms of like, have storms gotten stronger since the last 100 years? The jury's out. Have they, are there more storms? The jury's sort of out. There's not real strong evidence yet for a lot of that. I happen to be working on climate change and ice age and some of that stuff right now, so I'm looking at that pretty closely because I'm definitely interested in it. But now, you know, certainly superposed on the tide for sure, but that's very predictable.
Just to follow up on Bob's question, with the climate change, I think one issue that complicates the modern effort is the feedback effects, as well as the threshold effects.
The thing about climate models, and I've looked at a lot of those, because when climate models are working, you're trying to see if you can prove that changes that happened over thousands of years or sometimes hundreds of years make sense. It has to do with things like the changing conveyor belt, changing circulation in the North Atlantic, a whole bunch of different things. And when you try to mix models at different time scales, even trying to do climate models, you can't do as much detail because you're covering so much time, you'd never have fast enough computers to do it. So the climate models are pretty much separate from the short-term models that we use for forecasting weather, storm surges, and tsunamis, all those things. So it's two complete different time scales. And so it's whether, what the dean said, whether you're providing some kind of background difference that added onto it sort of makes a difference. Is there enough sea level rise that where your storm surge happened, that little bit of sea level rise made it just go over the levee? Well, you pretty much have to, you look at the tide data over the last 100 years, in some cases the sea level rises because the land's sinking. If you go to Chesapeake Bay, it looks like sea level's rising like crazy, but the land's really sinking. Likewise in Louisiana, because of extraction of oil and some water, the land's sinking makes it look like sea level rise is even higher. So you have to take that out as well and just look at the global signal of this sea level rise. And right now, you know, we're still talking millimeters a year kind of a thing. And mostly from expansion of warming up the upper portion of the ocean. Most of the fresh water that came from the ice sheets of the last ice age have already been put into the ocean. So now the big thing is when I look at the danger signs, for example, let's say that it warmed up like crazy and the Greenland ice sheet started melting. It's going to take a while for that to melt. The more dangerous thing is if the lubrication under the sheet is increased and the whole thing just slips off and floats in the ocean like a giant ice cube, because that would raise the sea level just as much as if it all melted. So to me, that's really the only potential danger, yet lately they're showing that it speeds up in some places, it slows up in other places. It doesn't seem to be conclusive that it's going in that direction. So I think you can feel pretty safe at the moment. Now, it's different when things like the warming is changing, where the melting zones are in the Himalayas, and how that affects how much water is coming down the river and how much that affects growing seasons. Some of those things are a more obvious effect of climate change than like sea level rise. And I know I like to use that to scare you, but I don't think we have to worry about that for 50 years at least. Yeah.
Yeah, sorry, I somewhat disagree with what your take on this. When you say that climate change is happening slowly, it's happening slowly from the point of view of a human lifespan. But in terms of the time spans of time in which climatologists normally deal, it's happening extraordinarily quickly. So the specific question...
Well, I just want to interrupt and say you're absolutely right. The rate that CO2 is going up is sort of unprecedented.
No, not CO2, just the warming.
Yeah.
And so my question, to get to the specific point, and it has to do with storms and with storm surge, because without storms, no storm surge, right?
Yeah.
So measurements, and you mentioned you raised the importance of measurements, for example, by satellites, which we haven't had for that long.
Right.
We haven't had a very long trend, but having data from instruments that's validatable, as it were, we can validate and we can check, shows that sea surface temperature has been rising in a fairly sort of rapid kind of way, and the most recent knowledge that we have about the top 2 kilometers of the ocean shows that the ocean heat content has been increasing pretty rapidly too.
Right.
So my question is, in view of those data, the only way I think you can get around saying that this is not likely to be a problem in terms of causing stronger storms, and therefore stronger storm surge events, is if this is a purely cyclic phenomenon, and if we're going to lose, if that energy that's currently stored up in the ocean and the top 2, we only know about the top, I think definitely about the top 2 kilometers, which is quite a chunk of it, right?
Yeah.
You know, is that, the only way out of it is to say that that's cyclic, and at some point that energy will be dissipated somehow, but I don't know how it will be dissipated if not in storms.
Yeah, and I'm only basing that on when they try to look at the storm statistics and try to figure it out from data, and they haven't come up with any conclusions. Theoretically, you would think the more heat you get in the upper ocean, the more you're going to feed some hurricanes someplace, and that's going to make a difference.
Well, I think what they say is that the expectation is that the increased warmth is going to result in more shear, which will prevent the formation of hurricanes. So you're going to get fewer. But on the other hand, if you do get one, then this is the conventional knowledge, right?
Yeah.
The warmer ocean surface will provide fuel. You know, it's like rocket fuel. You know, if the temperatures.
Like if you get one, it's bound to be stronger.
Right.
Yeah.
And so it's the extremes which we worry about, because we're probably less well equipped to deal with really, really big storms than we are to deal with a sequence of smaller ones.
Right,
So
and it's going to depend on where the distribution of this increased heat is. If definitely your data is showing you it's down in the tropical areas where they are born versus the Arctic, which we know warms more than the rest of the world, versus, and because even in our pretty intensive world of measurements, is the spatial coverage enough in all places to really sort it all out?
Well, for the satellites it is, because you know, the satellite, that's the advantage of the satellites. I'm a remote sensing expert. So
Yeah,
something
yeah.
like one of the big advantages is they do look everywhere. You know, unless you're looking at the surface and you're using sunlight and you can't see through the clouds. But in many cases, we're using other wavelengths that can come
Right.
out. So we do have, I think, reasonably good records now. The criticism would be they're not very long. You know, Arctic sea ice, for example, we go back.
Right, so the short-term natural availability, you're not 100%
so
short on.
The argument you could say there, well, those data don't by themselves show that it's not cyclical. But I think the consensus is that it's definitely not cyclical. The whole phenomenon of warming is not cyclical. And so, you know, that's why I'm surprised to hear you say it's a slow phenomenon. You know, it doesn't seem to me to be something that scientists are saying, that this is a slow phenomenon, you know.
Yeah, I mean, and certainly when they started looking at so-called abrupt climate change, which even in terms of what you're talking about is long, because when you're going, you know, let's say you got a bunch of meltwater in North Atlantic and the conveyor belt stops for a while, and sometimes it's hundreds of years for that kind of stuff. So even their so-called abrupt stuff isn't as abrupt as what you're talking about. And that's what makes it unusual, and you can never say for certain what's really going to happen, but it's scary enough to worry about. And I start off in the sea level rise part and maybe extrapolate a little bit too broadly, but in the sea level rise part of it, I don't think it's a concern unless, of course, it heats around Greenland so much that that big thing comes off faster than it's coming off or something like that. But
Yeah, it's a good question about the sea level rise, because many people, if you talk about
That's-
climate change, the thing that people tend to highlight is
yeah.
sea level rise in cities, which is presumably a valid concern, but there's a whole range of other things.
I think it's kind of a mistake to scare people with that when there's other things that are more scary.
So, hold on, so what is more scary in your view than that? Just as you raise it.
I mean, even the stuff you're talking about is scarier than that. I don't know where it is on the scary scale, but and then looking in terms of, you know, impacts that may be not on, you know, deaths, but in terms of livelihoods, in terms of changing the way the water comes down the Himalayas and other mountain systems and stuff, and people, if the water is coming down well before the typical growing season, things like that. And if that's happening, typically things evolve and adapt, but if it's happening so fast you can't evolve and adapt, you know, what's going to happen? And is it going to be just third world countries that suffer, or what's going to? I mean, typically in the past, they love to talk about the coral reefs and the low-lying islands. In the past, it's been slow enough that it always adapted, you know. And I don't think sea level necessarily is going to rise fast enough that you can't keep up with it. I think it's more like local building and other things that are going to cause the problems, but you never know.
What about the atmospheric circulation changes and effects on the ocean?
Atmospheric deposition?
No, circulation.
Oh, that's even more complicated and difficult to figure out. I mean, even when they talk in terms of, let's say, the Arctic warming more and how it's changing the weather systems up there, I'm not the right person actually to answer that. You need an Arctic meteorologist or somebody like that.
Thank you for coming. We're going to have a book signing after the lecture. If you want to stick around.